Welcome. In this video, we will explore the fundamental concepts of kinematics, the study of motion. This topic is a core component of the IB Mathematics Analysis and Approaches higher-level curriculum. By the end of this session, you will be able to define and differentiate between key terms like displacement, velocity, and acceleration. You will also be able to use calculus to model and analyze motion in a straight line. We'll begin by establishing a precise language for describing motion. This will involve understanding the difference between scalar and vector quantities in the context of kinematics. Let's start with the language of motion. Imagine an object moving along a straight line. We need a way to describe its position and how that position changes over time. First, we have displacement, denoted by S. Displacement is the object's position relative to a fixed origin, which we'll call O. It's a vector quantity, meaning it has both magnitude and direction. If the displacement S is positive, the object is to the right of the origin. If S is negative, it's to the left. This sign convention is crucial for understanding direction. Next is velocity, denoted by V. Velocity is the rate of change of displacement. It's also a vector quantity. Its sign tells us the direction of motion. A positive velocity means the object is moving in the positive direction, which we've defined as to the right. A negative velocity means it's moving in the negative direction, or to the left. Finally, we have acceleration, denoted by A. Acceleration is the rate of change of velocity. It's a vector quantity that describes how the velocity is changing. A positive acceleration means the velocity is increasing. A negative acceleration means the velocity is decreasing. It's important to note that negative acceleration or deceleration doesn't necessarily mean the object is moving left. It just means its speed is reducing. Now, let's contrast these with their scalar counterparts. Distance traveled is a scalar quantity. It's the total length of the path an object has taken, regardless of direction. It always accumulates and is always non-negative. Speed is the scalar counterpart of velocity. It's the magnitude of the velocity vector. Speed tells us how fast an object is moving, but not in what direction. It is always non-negative. So, to recap, displacement, velocity, and acceleration are vector quantities that include direction, while distance and speed are scalar quantities that only describe magnitude. Let's formalize the relationships between these quantities using calculus. This is where the power of this approach becomes clear. If we have a function for displacement s of t, we can find the velocity function v of t by differentiating s of t with respect to time. Similarly, if we have the velocity function v of t, we can find the acceleration function a of t by differentiating v of t with respect to time. This means that acceleration is the second derivative of displacement with respect to time. We can also reverse this process using integration. If we have the acceleration function a of t, we can find the velocity function v of t by integrating a of t with respect to time. And if we have the velocity function v of t, we can find the displacement function s of t by integrating v of t with respect to time. Remember that integration introduces a constant of integration. To find this constant, we need an initial condition such as the initial displacement s0 or the initial velocity v0. This diagram summarizes the entire process. Differentiating moves us down the chain from displacement to acceleration, while integrating moves us up the chain. Let's apply these ideas to a classic problem. A stone is thrown from the top of a lighthouse. Its displacement above ground level is given by the function s of t equals negative 5t squared plus 20t plus 25 for t between 0 and 6 seconds. Our first task is to find the initial displacement of the stone. The term initial always refers to the time t equals 0. So, we substitute t equals 0 into our displacement function. This gives us s of 0 equals 25. The initial displacement is 25 meters. This means the stone was thrown from a height of 25 meters. Next, we need to find the time and place where the stone changes direction. An object changes direction when its velocity is 0 and its acceleration is non-zero. First, let's find the velocity function by differentiating the displacement function. v of t equals the derivative of s of t, which is negative 10t plus 20. Now, we set the velocity to 0 to find the time when the stone is momentarily at rest. Solving negative 10t plus 20 equals 0 gives us t equals 2 seconds. This is the time when the stone changes direction. To find the place or displacement at this time, we substitute t equals 2 back into the original displacement function. S of 2 equals 45 meters. So, the stone changes direction after 2 seconds at a height of 45 meters. Finally, let's find the time interval during which the stone is above ground level. This means we need to find when the displacement s of t is greater than 0. We set s of t greater than 0. We can factor the quadratic to find its roots. The roots are t equals 5 and t equals negative 1. Since time cannot be negative, we are interested in the root at t equals 5. The parabola opens downwards, so the displacement is positive between its roots. Considering our domain of 0 to 6 seconds, the stone is above ground level for the interval from t equals 0 to t equals 5 seconds. Now, let's delve deeper into velocity. We'll distinguish between average velocity and instantaneous velocity. Average velocity is the change in displacement over a time interval. It's calculated by taking the final displacement minus the initial displacement and dividing by the final time minus the initial time. Visually, on a displacement time graph, the average velocity is the gradient of the chord connecting the 2 points corresponding to the start and end of the time interval. Instantaneous velocity, on the other hand, is the velocity at a single moment in time. As we've already established, it's the derivative of the displacement function, v of t equals s prime of t. Graphically, the instantaneous velocity at a specific time t is the gradient of the tangent line to the displacement time graph at that point. Let's work through an example to solidify this. A particle moves with displacement s of t equals 3 minus t squared. We need to find the average velocity from t equals 2 to t equals 5, and the instantaneous velocity at t equals 2. For the average velocity, we use the formula. We calculate s of 5 and s of 2. S of 5 is negative 10 and s of 2 is 2. Plugging these into the formula gives us negative 4 meters per second. The negative sign indicates the average motion was to the left. For the instantaneous velocity, we first find the velocity function by differentiating s of t. This gives us v of t equals 3 minus 2t. Then we substitute t equals 2 into this function. V of 2 is negative 1 meter per second. At that exact moment, the particle is moving to the left at 1 meter per second. We've seen how to find displacement from velocity using integration. Now let's explore how this relates to distance traveled. The change in displacement over a time interval from t1 to t2 is given by the definite integral of the velocity function over that interval. This integral represents the net change in position. If the velocity is always positive over the interval, the object never changes direction. In this special case, the change in displacement is equal to the total distance traveled. However, if the velocity changes sign, the object reverses direction. The integral of v of t will give the net displacement, which is not the total distance. To find the total distance, we must integrate the absolute value of the velocity, which is the speed. Let's look at an example where the object changes direction. A particle moves with velocity v of t equals t squared minus 3t plus 2. We need to find the total distance traveled in the first 4 seconds. First, we need to find when the particle changes direction. This happens when v of t equals 0. Factoring the quadratic gives us t equals 1 and t equals 2. These are our critical points. Now, we need to find the displacement at these critical times and at the start and end of our interval. We integrate v of t to get s of t. Assuming the particle starts at the origin s of 0 is 0, we find s of 1, s of 2, and s of 4. Let's visualize this with a motion diagram. The particle starts at 0, moves right to 5, 6, then reverses and moves left to 2 to 3, then reverses again and moves right to 5 and 1, 3. To find the total distance, we add the lengths of each segment of the journey. The distance is 5, 6 plus the absolute value of the change from 5, 6 to 2 to 3, plus the absolute value of the change from 2 to 3 to 5 and 1, 3. This gives a total distance of 5 and 2, 3 meters. Alternatively, we can use the integral of the absolute value of velocity. We split the integral at the points where v of t is 0. This gives us the same result, confirming our answer. Let's now consider a more complex scenario involving exponential functions, which are common in IB problems. A train starts from rest at a station. Its acceleration is given by a of t equals 1/2 e to the power of negative t over 100. We need to find its velocity function and sketch its graph. To find the velocity function, we integrate the acceleration function. The integral of e to the power of negative t over 100 is negative 100 e to the power of negative t over 100. Multiplying by 1/2 gives us negative 50 e to the power of negative t over 100, plus our constant of integration, c. Now we use the initial condition. The train starts from rest, which means its initial velocity is 0. So v of 0 equals 0. Substituting t equals 0 into our velocity function, we get negative 50 plus c equals 0, which means c equals 50. Therefore, the velocity function is v of t equals 50 minus 50 ce to the power of negative t over 100. To sketch the graph, we can analyze its behavior. At t equals 0, v of 0 is 0. As t approaches infinity, the exponential term approaches 0, so v of t approaches 50. The graph starts at the origin and increases, approaching a horizontal asymptote at v equals 50. Part B asks how long it will take for the train to reach a speed of 40 meters per second. We set our velocity function equal to 40 and solve for t. Rearranging the equation, we get e to the power of negative t over 100 equals 1/5. Taking the natural logarithm of both sides, we find that t equals 100 times the natural log of 5, which is approximately 160.9 seconds. Finally, part C asks how far the train travels in this time. Since the velocity function is always positive, the train never changes direction. Therefore, the distance traveled is simply the definite integral of the velocity function from 0 to 100 ln phi. We integrate v of t to get the displacement function s of t. Evaluating this from 0 to 100 ln 5 gives us 5,000 ln 5 minus 4,000, which is approximately 447 meters. This is the total distance the train travels to reach a speed of 40 meters per second. Let's conclude with a final example that brings together all the concepts we've discussed: displacement, velocity, acceleration, and total distance. A particle moves with displacement s of t equals t cubed minus 6 squared plus 9t minus 1. We will analyze its motion in the first 3 seconds. First, let's find the velocity and acceleration functions. Differentiating s of t gives v of t equals 3t squared minus 12t about plus 9. Differentiating v of t gives a of t equals 6t minus 12. To understand the motion, we'll use sign diagrams for velocity and acceleration. The velocity is 0 at t equals 1 and t equals 3. The acceleration is 0 at t equals 2. Let's describe the initial conditions at t equals 0. The displacement is negative 1, so the particle is 1 centimeters to the left of the origin. The velocity is 9, so it's moving right at 9 centimeters per second. The acceleration is negative 12, so it's decelerating. The particle changes direction when the velocity changes sign. From our sign diagram, this occurs at t equals 1 and t equals 3. Let's find the position at these times. S of 1 is 3 centimeters, and S of 3 is negative 1 centimeter. Let's visualize this with a motion diagram for the first 3 seconds. It starts at negative 1, moves right to 3, then reverses and moves left back to negative 1. Finally, let's find the total distance traveled in the first 3 seconds. We add the distances of each segment. From t0 to t1, it travels from 1 to 3, a distance of 4 centimeters. From t1 to t3, it travels from 3 to 1, a distance of 4 centimeters. The total distance is 4 plus 4, which is 8 centimeters. We have now covered the core concepts of kinematics using calculus. You should be able to define and differentiate between displacement, velocity, and acceleration, and use differentiation and integration to solve problems involving motion in a straight line. To help you practice and master these skills, here are 5 IB-style practice questions. Pause the video, work through them, and then resume to see the fully worked solutions. Question 1. A particle moves with velocity v of t equals 1 minus 2t. Find the total distance traveled in the first second. Question 2. A particle is initially at the origin and moves with velocity v of t equals t squared minus t minus 2. Find its displacement after 3 seconds. Question 3. A ball is thrown from 1 meter above ground level. Its velocity is v of t equals 29.4 minus 9.8 t. Find the maximum height reached by the ball. Question 4. An object has velocity v of t equals cos of 2t. Show that the particle oscillates between 2 points and find the distance between them. Question 5. A particle is initially stationary at the origin. It accelerates according to a of t equals 2 over the quantity t plus 1 cubed. Find its velocity function. Let's go through the solutions. For question 1, we need to find the total distance traveled by a particle with velocity v of t equals 1 minus 2t in the first second. First, we find when the particle changes direction by setting v of t to 0. This gives t equals 0.5 seconds. This is within our interval of 0 to 1 second, so we must integrate the absolute value of velocity. We split the integral into 2 parts, from 0 to 0.5 and from 0.5 to 1. In the first interval, v of t is positive, so we integrate v of t. In the second interval, v of t is negative, so we integrate negative v of t. Integrating and evaluating, we find that the distance traveled in the first interval is 0.25 centimeters, and in the second interval is also 0.25 centimeters. The total distance is 0.5 centimeters. For question 2, we need to find the displacement of a particle after 3 seconds, given its velocity function and initial position. We are given the velocity function v of t equals t squared minus t minus 2, and the initial condition that the particle is at the origin, so s of 0 equals 0. To find the displacement function s of t, we integrate v of t. This gives us t cubed over 3 minus t squared over 2 minus 2t, plus a constant of integration, c. We use the initial condition s of 0 equals 0 to find c. Substituting t equals 0, we find that c must be 0. So, the displacement function is s of t equals t, cubed over 3 minus t squared over 2 minus 2t. Finally, we find the displacement after 3 seconds by substituting t equals 3 into our displacement function. This gives us negative 1.5 centimeters. The negative sign tells us the particle is 1.5 centimeters to the left of the origin. Question 3 asks for the maximum height reached by a ball thrown from 1 meter above ground level with a given velocity function. The velocity function is v of t equals 29.4 minus 9.8 t. The initial height is 1 meter, so s of 0 equals 1. The maximum height is reached when the ball momentarily stops moving upwards, which means its velocity is 0. Setting v of t to 0, we find that t equals 3 seconds. Now we need to find the displacement function s of t. We integrate v of t to get 29.4t minus 4.9 squared plus c. Using the initial condition s of 0 equals 1, we find that c equals 1. So s of t equals 29.4t minus 4.9 squared plus 1. Finally, we substitute t equals 3 into s of t to find the maximum height. This gives us 45.1 meters. So the maximum height reached by the ball is 45.1 meters. Question 4 asks us to show that a particle with velocity v of t equals cos of 2t oscillates between 2 points and to find the distance between them. First, we find the displacement function s of t by integrating v of t. This gives us 1/2 sin of 2t, plus a constant c. Let's assume c is 0 for simplicity, which means the particle is at the origin when t equals 0. The sine of function oscillates between a maximum value of 1 and a minimum value of negative 1. Therefore, s of t will oscillate between a maximum of 1/2 and a minimum of negative 1/2. This shows that the particle oscillates between the points s equals negative 1/2 and s equals 1/2. The distance between these 2 points is the difference between the maximum and minimum displacements, which is 1 meter. Finally, for question 5, we need to find the velocity function for a particle that starts stationary at the origin and has a given acceleration function. The acceleration is a of t equals 2 over the quantity t plus 1 cubed. The initial conditions are s of 0 equals 0 and v of 0 equals 0. We need to find the velocity function v of t. To find the velocity function, we integrate the acceleration function. We can rewrite a of t as 2 times the quantity t plus 1 to the power of -3. Using the power rule for integration, we get -1 over the quantity t plus 1 squared plus a constant c. Now we use the initial condition v of 0 equals 0 to find c. Substituting t equals 0, we get -1 plus c equals 0, which means c equals 1. Therefore, the velocity function is v of t equals 1 minus 1 over the quantity t plus 1 squared. This function shows that the particle starts at rest and its velocity increases, approaching a limiting velocity of 1 meter per second as time goes on. That concludes our exploration of kinematics using calculus. We have defined the key terms, established the relationships between them through differentiation and integration, and worked through several examples, including those with changing direction and exponential functions. Remember, the ability to translate a physical description of motion into a mathematical model and solve it using calculus is a fundamental skill in IB mathematics, HL. Keep practicing these types of problems to build your confidence and mastery. Thank you for watching.